What's up, guys? Today we're doing a question on Leetcode currently being asked by Dropbox and Amazon, and the question is called Game of Life. Let's get to it. Hey guys, so just to jump into the problem description is, according to the Wikipedia article, the game of life, also simply known as life, is a cellular automation devised by the British mathematician John Horton Conway in 1970. Given a board with m by n cells, each cell having an initial state live 1 or dead 0, each cell interacts with its 8 neighbors using the following 4 rules. 1. Any live cell with fewer than 2 live neighbors dies as if caused by underpopulation. 2. Any live cell with 2 or 3 live neighbors lives on to the next generation. 3. Any live cell with more than 3 live neighbors dies as if caused by overpopulation. And 4. Any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. Write a function to compute the next state after one update of the board given its current state. The next state is created by applying the above rules simultaneously to every cell in the current state where births and deaths occur simultaneously. So we're given this input and output. I'm going to put it on line 5. The follow-up is, could you solve it in place? Remember that the board needs to be updated at the same time. You cannot update some cells first and then use their updated values to update other cells. And 2, in this question, we represent the board using a 2D array. In principle, the board is infinite, which would cause problems when the active area encroaches the border of the array. How would you address these problems? So for this example input given, we're just really looking at the current state and then all of the neighbors. And basically, we're just going to look at these like 4 rules. So for example, at index 1,1 on line 7, which is 1, that's going to be turned into 0 in the next state because it only has 1 neighbor, and because of that, rule 1 would apply because there's less than 2 neighbors. So the way we can do this, the way we can do this in place is that we can just use the space that we currently have. So we're just going to loop over our board, and then we can just find the number of neighbors. So live neighbors, get live neighbors at our current I and j. And then like another way we could do this is we could just have a neighbors matrix that is a copy of our current matrix and store each live neighbors value at that index. But the way we can do this in place is that we could just say our board at I at j is equal to the tuple of our current board at I at j and our number of live neighbors. And then through using this tuple, we don't have to create any new matrix, and we can solve this in space. So the way we're going to do this is we're just going to first loop over, create this tuple that has cur state, comma, live neighbors, and then we're going to loop over one more time, and we're going to check all the cases, and we're just basically going to write out these cases. And then if one applies, then we're going to change it, and if none of them apply for the cell that we're at, we're just going to keep it what it currently is. So our current state is equal to our board at I at j at 0, and our number of live neighbors is equal to board at I at j at 1. And let me fix this really quick. So now we just basically need to write out these cases. So the first case is if the cell is live, and we can say if current state because 1 would evaluate to true, and live neighbors is less than 2. We can set it equal to 0 because it would die as if caused by underpopulation. And now we can just write out these other cases. So elif current state, and we have between 2 and 3. So 2 is less than or equal to live neighbors, which is less than or equal to 3. It's going to live on. And then our case 3 is any live cell with more than 3 live neighbors dies as if caused by overpopulation. So we can say greater than 3, and this cell would die. And then our fourth case would be if not current state because 0 would evaluate to false, and it has exactly 3 live neighbors, then it's going to become live as if by reproduction. And then in our last case, if this doesn't fit one of the cases, we're just going to set it equal to its current state because there's no reason to change it. So current state. So now all we need to do, because we don't need to return anything, is we can just create this get live neighbors function. And I wrote this as a closure. And what a closure is it's a private function inside a first class function, the first class function being my game of life function, which like basically just lets me use all of the variables in the game of life function. So because it's a closure, I can like look at the board and see that without actually passing that in. So, and because I think that I'm not going to need to use this function for anything else in the future, it's just easier to write this way. But you could also write this as its own first class function. So what I'm going to need to do here is I'm going to set my number of live neighbors equal to 0 and then return the number of live neighbors. And then I'm going to need to look in every single direction. So for x, y in the 8 directions, and I'm going to do up, down, left, right, up and to the right, down and to the left, right and down, up and to the left. So that looks like 8, 1, 2, 3, 4, 5, 6, 7, 8. Sweet. So now what I need to do is I need to get my temp I, which is equal to x plus I, and my temp j, which is equal to y plus j. And then I need to see if this is in the bounds of my matrix, so I don't get an index out of bounds. So if temp I is less than 0, or temp j is less than 0, or temp I is greater than or equal to len board, or temp j is greater than or equal to len board at 0, then I can just continue and skip everything else that's going to happen. Otherwise, I can say red plus equals my board at I at j. But because I'm going to be changing these into tuples on line 42, I'm going to want to check and see if it's been changed into a tuple yet. So board at I at j, and this is actually going to be temp I, temp j, if board at if the type of board at I at j is still an integer, equals type of integer. Otherwise, I'll just add my type. I'll just add my board at temp I at temp j at index 0, because I know that's where my current state is, and then I'll return that red. So cool. If there's no errors in the way I coded this, this should be good to go. Let's see if there's any problems. So for j in range, len board at 0. Oh, board is not defined, so change this to board. Board is not defined again. Let's see if there's any more bodes. Great, and this looks good. Great, nice work. So cool, I hope that made sense, guys. If you have any questions, just leave them in the comments down below. This is a really good question for understanding breadth first search and then working in space with matrices. So let me know if you have any questions about it, and let me know if you want to see any more videos like this in the future. I'll catch you again soon. Have a good one, guys. Peace. I don't really care if you cry.